Hi everybody, so we're going to be deriving the area of a circle in this video, which is pretty simple. Here I've considered a circle of radius capital R, and I've considered a strip of area in the circle which inscribes an angle d theta at the center, and which is an angle of theta with respect to this horizontal line. Now it should be intuitive that to obtain the area of the entire circle, we need to add up the areas of these small individual strips. But as I'm considering to be very small, I can transform that addition into an integration, because it's going to be continuous. It's not discrete values. It's continuous from theta equals 0 to theta equals 2 pi, which is 360 degrees. So I need to know the area of this small strip, right? And I'm gonna write that down as dA, and that area can be obtained by considering this strip as a triangle because the area is pretty small. So for this triangle that has an angle d theta over here, and yeah, this is the arc length, and the arc length is shown by x. So if this is the arc length x, then I can get the area of this triangle by getting a perpendicular line from the top vertex to the base x. And the length of this line, or the dimension of this line, should be the same as r, because this angle is very small, and so should be the dimension of the sides of the triangle. So all of these will be r because this angle is very small. So you can assume the entire dimension to be r. Alright, so now for this triangle, the area can be written as half times base times the height. Base here is x, times height here is r. So the area dA should be half times x times r. So I'm going to write that down here. dA should be half times x times r. Right, that is the area of this small strip. Now here I have a quantity x, which is the arc length. I'm going to convert that in terms of theta so that I can integrate it from 0 to 2 pi. So from another definition of trigonometry, for the small angle d theta, you can write it down in terms of arc length as d theta equals x over r. So this d theta is x over r. Alright? So x can be written as r times d theta. That is the value of x here. And I'm going to substitute that right into our previous equation to get a value of dA in terms of d theta. Half times r d theta times r, which is half r squared times d theta, right? So now you have this as the value of dA, and which is the area of a small strip. Okay, so I have dA. Now I need the net area, A. If I have the small area of this strip, I can obtain the net area of this entire big circle by integrating it from 0 degrees to 360 degrees, or 0 to 2 pi. So I'm just going to keep the expression that we just derived, the last expression. I'm going to get rid of the rest of it. Okay, so now you have this expression of area, dA equals that, and to obtain the, I'm gonna have to write that down here again. dA equals half r squared d theta. So this is the expression for dA. So total area should be integration from 0 to 2 pi, or 360, times half, well, no times, just integration of this function, half r squared d theta, right? Which, in other words, is half r squared times integration of d theta, 0 to 2 pi. Integrating this small angle d theta from 0 to 2 pi should just be half r squared times theta with limits of 0 to 2 pi, right? 0 to 2 pi. Those are the limits. And now this becomes half r squared times 2 pi minus